Hello everybody, it's Untitled Jiaozai. Welcome back. And here's an item from geometry, from the CEMC of Canada in their FIRMA contest. The vertices of an equilateral triangle lie in a circle with radius 2. Find the area of the triangle. As usual, pause this video and give it a try. And if you're done, let us dive into the solution. Now, Dumplet over here has provided two solutions. One involves the use of formulas in geometry, and the other one involves trigonometry. Let us start with the geometrical solution first. I'll be introducing to you guys two formulas that you guys may use in future math problems that you encounter. So let's start with this figure. Suppose we let the triangle be ABC. And let's have center O here, or the circumcenter of triangle ABC. Since O is the circumcenter, then AO should have a length of 2. Now, we may use the formula for the circumradius R of a triangle with sides A, B, and C. Now, this formula is used in a lot of math competitions. So the circumradius R is equal to ABC over 4 times the area of the triangle. Now in this case, we have an equilateral triangle, so we'll be able to get the sides easily. If we have one side to have S, then ABC would simply be S times S times S, which would be equal to S cubed. So our only problem now is the area. So apart from this formula, I'm going to introduce to you the second formula. Now we may use the formula for the area A of an equilateral triangle, right? So since there's only one side length in an equilateral triangle, we have the formula in terms of the side length. So side length S. So the area of an equilateral triangle with side length S is given to be S squared square root of 3 all over 4. So we'll be using two formulas to help us with this item. Now obviously there are a lot of other approaches, but this is the solution that Dumplet wants to show you because it involves formulas that you guys may use in future math problems. So since we know what A, B, C are, they're just S, S, and S. So let us put this formula for the area into our formula for the circumradius R above. So we have the following. Since we have A, B, C equals S and R equals 2, we can substitute them here. Alright, so we have R equals 2, and then A, B, C equals S cubed. Now we have 4 times the area. Now we simply substitute the formula for the area here. That's what we have here. And we simply solve for S. Now the 4's here cancel. The S cube and the S square will cancel, leaving just S at the top. So this will actually give us 2 equals S over simply square root 3. Now multiply both sides by square root 3. We are going to get that S equals 2/3. Now this is the side length of the equilateral triangle. But the problem asks us to get the area of the triangle. Now it's very convenient for us to simply substitute this value of S here because we have the formula for the area in terms of S. So we substitute into the formula for the area. This is the value of S, 2 square root 3. So the area equals side squared to 2 square root of 3 quantity squared, square root 3 all over 4. Now 2 square root of 3 quantity squared is 12. So 12 square root of 3 all over 4. So we can cancel the 12 and the 4, leaving only 3 at the top. So the area is 3 square root 3. And this is indeed the final answer. Now, this is the geometrical approach, and now I'm going to tell you, or to show you, the trigonometric approach. And this is a little bit shorter, but maybe it's because of the given item. But hopefully you guys will be able to understand both solutions and understand the use of the formulas presented in the two solutions. Now, for the trigonometric approach. We may also use trigonometry to solve this item. Note the formula for the area of the triangle given two sides with lengths A and B and the angle between them, theta. Note that theta here is an angle, so we can express it, or we can express the area in terms of 1/2 times AB times sine of the angle theta. So let us use this solution in this item. Now, because we do not know what the side lengths are, we are unsure what the side lengths are. So it would be practically impossible for us to get what the side length is without going through the geometric solution. But we do know that O here is the circumcenter. So if I connect B and O and C and O, I know that they would also have a length of 2. Now the good thing about this is that I have two sides in triangles AOC, in triangle AOB, and triangle OBC. So it would be very convenient for us if we knew what these three angles were. And in fact, we do, because this is an equilateral triangle, so we know that one circle is, one rotation, or one full rotation, is 360 degrees. Since it's split into 3 equal regions, we know that these would be, these three angles would each be 120 degrees. So this is always the case in an equilateral triangle, since everything is symmetric anyway. So you can simply divide 360 degrees for one revolution divided by 3 to get 3 lots of 120 degrees. Now, why is this helpful? It's because we can get the areas of triangle AOC, we can get the area of triangle BOC, and we can get the area of triangle AOB via the trigonometric formula for the area. Because I have two sides, let's take the case in triangle AOC. I have AO and OC, and I have the angle in between. In triangle BOC, I have BO and OC and the angle in between. In triangle AOB, I have AO, BO, and the angle in between. And in fact, these three triangles, AOC, BOC, and AOB, they're actually congruent. So we can actually just get one of the areas and then just multiply it by 3. So let's do that. Going back to the figure, let's just use AOC. We know OC equals 2, and we know that this angle is 120 degrees. From the formula, the area equals 1/2 AB times C. We can just have A equals 2 and B equals 2. Doesn't really matter which is which. And we have the value of theta here, which is the angle between the two sides of side length 2. So 1/2 times 2 times 2 times sine 120. Now note that we have the value of sine 120 to be square root of 3 over 2, since 120 is a special angle, so do remember this. So 1/2 and 2 will have a cancel, the 2 will cancel, the 2 and the square root 2, the 2 and the 2 here from sine 120 will also cancel, giving us the area of one triangle, particularly AOC, to be square root 3. Now since I've mentioned a while ago that we have 3 congruent triangles here, so I'll just take whatever the area of triangle AOC is and multiply it by 3. So let's multiply both sides by 3. So we have 3a equals 3 square root of 3. And this would be the sum of the 3 triangles AOC, BOC, and AOB, which gives us the entire area of triangle ABC. And this is the exact same answer that we got from the geometric approach.